Hi. In the past couple of modules, we've been talking about model building. We're talking about how to get a good design matrix for the GLM. Now, in this module, we'll talk about GLM estimation. So again, to recap, a standard GLM can be written on the following format. We have Y, which is the fMRI data, X, which is the design matrix, which we learned how to build in an appropriate manner in the previous modules. And we have beta, which are the regression coefficients, and epsilon, which is the noise. So now what we're primarily interested in is learning how we can estimate beta from this model. So let's, for simplicity, first assume that epsilon is normally distributed with mean 0 and is IID, the individual epsilons. So it's the variance-covariance matrix is the identity times sigma square. So here we're primarily interested in estimating beta and sigma squared. So here the matrices X and the vector Y are assumed to be known, and the noise is assumed to be uncorrelated. So at the end of the day now, in the GLM, our goal is to find the values of beta that minimize Y minus X beta transpose Y minus X beta. This is the sum of squared errors, or SSE. So to put this into kind of context, we can think about this when we have one column in our design matrix, and this is simple linear regression. So we have Y on the Y-axis and X on the X-axis, and so we want to find the line that best fits this data. So in the least square sense, that line is the line that makes the distance from the points to the line in the Y direction, so the E1, E2, and E3, the squared of those residuals as small as, the sum of the squared of those residuals as small as possible. In two dimensions, when we have two explanatory variables, x1 and x2, we look for a plane, and we try to find a plane that best fits this cloud of data. When we have a design matrix with p columns, we want to find a p-dimensional hyperplane that best fits this data. So the least squares criterion, we're going to write this as Q equal to this least squares. And what we want to do is we want to find the values of beta that make this as small as possible. So one way to do that is to take the derivative with respect to beta and set the result equal to 0. This gives us the so-called normal equations, which is x transpose x beta hat equal to x transpose y. So by solving for this, we get the ordinary least squares solution, which is the following. Beta hat is equal to x transpose x inverse x transpose y. So that's a key equation when talking about the GLM. That's our kind of standard estimate for beta hat. So since x and y are both known a priori, we can find this estimate quite easily using our design matrix in our data. So the ordinary least squares solution has a number of interesting properties. First, it's the expected value of beta hat is equal to beta, so it's an unbiased estimator. So on average, beta hat gives us a good estimate of beta. And also, the variance of beta hat is equal to sigma squared times x transpose x inverse. So what does that mean? Well, it turns out that according to something called the Gauss-Markov theorem, any other unbiased, if you think of all the other possible estimators of beta that are unbiased, any other unbiased estimator of beta is going to have a larger variance than the OLS solution, the ordinary least square solution here. So any unbiased estimate that we have will have a larger variance than the variance of beta hat. And so we call beta hat the best linear unbiased estimator, or BLUE. So again, to sort of recap here, if epsilon is IID, then the ordinary least squares estimate is optimal in this best linear unbiased sense. So in this case, we have the model y is equal to x beta plus epsilon, and we get the following least squares estimate. So if the variance of epsilon is not IID, if epsilon is not IID, and the variance of epsilon is equal to v sigma squared, which is not equal to the identity, then we instead have to use something called the generalized least squares estimate, and that's going to be the best linear unbiased estimator. So in that setting, we also have to include estimates of v when computing beta hat. So in that case, beta hat becomes x transpose v inverse x inverse x transpose v inverse y. So basically what happens here is we have to include the variance covariance matrix into our estimate of beta. Now you'll see that this is a special case of, that ordinary least squares estimation is a special case of this, because if you put in v equal to identity, the solution, the estimate becomes the ordinary least squares solution. So basically, when we have autocorrelated epsilon, the OLS is not the optimal solution anymore, and we need to use this generalized least squares solution instead. So here's again a recap. So we have the model here, and this is the generalized least squares estimate, and so that gives us the fitted values y hat, and using these fitted values we can compute the residuals as follows. And here, the capital R is what's called the residual inducing matrix. So it's just sort of a notation that we often use in statistics to say that this is a way of taking the data and moving it into the residual space. So even if we assume that epsilon is IID, we still need to estimate the residual variance as sigma squared. And so our estimate of sigma squared is going to be based on the residuals. So it's the residuals, the transpose of the residuals times the residuals, so R transpose R, divided by the trace of the residual inducing matrix and V. And so in our setting, in the OLS setting, our sigma hat squared is going to be R transpose R divided by capital N, which is the length of Y, minus P, which is the number of columns in the design matrix. So this might be familiar if you've taken a linear regression class. However, if V is not equal to identity, so we have autocorrelated noise, things become more difficult, and that's the focus of the next module.
Understanding estimation allows us to understand the GLM in a geometric way. So let's think of y, the dependent variable, as a vector in the space with one dimension per observation, usually per subject. So now imagine a data set with 3 subjects. There are 3 dimensions in y. So y is a vector in 3-dimensional space. Let's also imagine we have a model with 2 parameters, 2 regressors. That means that the model space spans 2 dimensions. And what we can see here is a frame with 3 dimensions for y, and the 2 dimensions that define the subspace of the model. Now, any 2 parameters, all possible linear combinations of those parameters, span a plane. And so what we see here is the plane is the subspace that is spanned by the model. Now, what are we doing when we fit the linear model? The goal is to minimize the sums of squared errors, as you see here. So now I've color-coded the error vector in red, and the original data in blue, and then the fit in green. And what we're seeing here is when we solve for beta, we calculate beta hat as x transpose x inverse x transpose y, and what this is doing is projecting the data y onto the subspace that's defined by the columns of x. So I like to think of projection as shining a light source. Imagine a light at the top of the frame you see there, and the light shining down, and it's shining past y. Imagine y is sort of a solid bar, and it's shining down onto that plane that's defined by the model subspace. Now y is going to cast a shadow that's as close as you can get to the data in the model subspace. And that shadow is the fit. That's the green line, the dark line in the plane. And that is the projection of y, the data, onto the model subspace spanned by x. And so it turns out this matrix here, which is also sometimes written as x minus y, so pseudo-inverse of x, is the matrix of a projection onto a subspace. So that's the end of this module on estimation.